Looking at the orbital diagram of carbon, we see that it has two paired electrons in the s orbital and two unpaired electrons in the p orbital. We know that the p orbitals are aligned along the px and the py axis, and we would expect that these bonds would be 90 degrees from each other because they are along the x-axis and the y-axis. However, what we observe is we see four bonds that are 109.5 degrees apart from each other. The reason for this is when we take the atoms and put them into molecules, our orbitals do something called hybridization, or they hybridize. So when our molecules are formed, the orbitals hybridize to maximize their bonding. The more bonds they make, the more full orbitals they have, the more stability that there is for the atom or the molecule. And so what happens is we actually mix different types of orbitals in the valence shell to make a new set of orbitals. And we have lots of different possibilities that we can do. We can have the 1s and 1p hybridize to make sp, 1s and 2 of the p to make sp2, 1s and all 3 of the p to make sp3. We can start adding some d orbitals in if we have more than 8 valence electrons. So we can have sp3d and sp3d2. Now, it depends on how the atom is bonded as to the different types of hybridization that it can have. So carbon can have 3 different types of hybridization. It can have sp, and that happens when we have 2 electron groups. So there's different ways we could do that, but one example is 2 double bonds to carbon. This would be an sp hybridization because we have 2 electron groups around that carbon. We could have sp2 hybridization, which happens when we have 3 electron groups. So this would be, an example would be carbon double bonded to oxygen with 2 single bonds. So because we have 3 electron groups, we need 3 orbitals to combine. So it would be sp2. And if we want sp3, then we would have 4 single bonds to carbon, 4 electron groups. We need 4 orbitals to mix. So we would have 1s and 3p mixing to give us a total of 4 orbitals to put our 4 electron groups into. So let's look at the different hybridizations. If we have 2 electron groups around the center atom, we're going to need 2 orbitals to mix, which is sp hybridization. This gives us a linear electron geometry with 180 degrees between our bonds. If we have 3 electron groups, we need 3 orbitals, 1s and 2 p's that are mixing, which we call sp2 hybridized. This is a trigonal planar shape with 120 degree bond angle. So by forming these hybrid orbitals, we end up with our observed geometry. We have 4 electron groups. We need 4 orbitals, 1s and 3 p's to give us sp3 hybridization. This is a tetrahedral electron geometry with 109.5 degree bond angle. 5 electron groups is trigonal bipyramidal. Now we have to start adding D's into the hybridization because we have 5 electron groups. So this is sp3d. And we do end up with the 90 degree bond angle between our axial and equatorial bonds and 120 between the equatorial. 6 electron groups is octahedral, sp3d2 with 90-degree bond angles. So you can determine the hybridization based on the number of electron groups that you find around your center atom. Using one orbital for each electron group, we always start with S and continue from there. Our hybridized orbitals can result in different types of bonds, and the two types of bonds are sigma bonds and pi bonds. Sigma bonds are any single bond that we see in a molecule. And this happens when we have lots of different types of interactions. So it can be s orbitals that are overlapping to share their bonds. It can be p orbitals that are overlapping to share their electrons, or hybrid orbitals overlapping with each other, or an s that is overlapping with a hybrid. So there's lots of different ways that we can form sigma bonds. To form a pi bond, we have to have p orbitals that are unhybridized that are overlapping next to each other. And so pi bonds are the second bond in a double bond, or the second and third bond in a triple bond. So the first one is going to be a sigma, but the second and third are going to be a pi. And this interaction, it's not as strong, so the pi bonds are not as strong as the sigma bonds. So they're a little bit easier to break, but when we have multiple bonds, they're stronger than just one single bond. So they do add together. The pi bonds are easier to break, but a sigma and a pi together are stronger than a sigma. So in order to form a pi bond, our p orbitals need to overlap shoulder to shoulder. They need to be parallel with each other, and the electrons that are shared in these parallel orbitals form a pi bond. If our p orbitals overlap head to head, then it is a sigma bond. So the only instances where we form pi bonds are if we have unhybridized p orbitals that overlap shoulder to shoulder. And this happens when we form double bonds and when we form triple bonds. Here we have two different examples. We have dichloroethane, ane meaning that it's all single bonds, and we have dichloroethene meaning that it has a double bond. If we have only single bonds, so our orbitals are overlapping head to head, we're sharing the electrons in this sp3 hybridized orbital, our molecule can freely rotate. So the chlorines, they could be next to each other, they could be opposite each other at any given point in time. That bond can rotate around freely. However, if we have a double bond that forms from our unhybridized p orbital, we form a pi bond. So we have a sigma bond in the center, and we have a pi bond that forms in our unhybridized p orbital. So we've got our pi bond. That locks the molecule into place. So it cannot freely rotate. It is stuck in one position. And because it gets stuck in one position, we have differences depending on the side of the bond that our chlorines are found. If the chlorines are found on the same side as each other, that is what we call a cis bond. So if we draw a line through our double bond, the chlorines are on the same side as each other, that is cis. If we draw a line through our double bond and our chlorines are on opposite sides as each other, that is trans. And these are two different molecules that have slightly different properties because of the arrangement of the chlorine atoms. And again, this comes from the sigma and the pi bond. So in this case, our dichloroethane, every single bond is going to be a sigma. The first bond in our double bond is a sigma, and we have 1 pi. So we would have 5 sigma bonds and 1 pi. It's the same for the trans, but do note, okay, the different molecule because our chlorines are on opposite sides of the bond. So if we think about this, our cis molecule is going to be more polar. Our trans bond is going to be nonpolar. It's going to have a smaller dipole moment because it is more symmetrical. Our cis bond is less symmetrical. We're going to have more electronegativity next to the chlorine, less electronegativity, delta, not sigma, less electronegativity next to the hydrogen. So let's try an example. We're going to predict the hybridization and the bonding scheme for CH3CHO. And again, we have a condensed formula for our molecule. So when we draw this, these 3 hydrogen are connected to the carbon. This hydrogen is connected to the carbon, and the oxygen is connected to the carbon because it follows that carbon. If we count we'll double check by doing an electron count, but that oxygen is going to be double bonded because our carbon needs 4 bonds. But let's check our electron count. So 4 for each carbon, 1 for each hydrogen, and 6 for the oxygen. So we have 18 electrons to work with. The way we have it drawn, we have 14 electrons in the bond and 4 electrons in the lone pair of the oxygen. So we do have this molecule drawn correctly. Now, if we look at our hybridization, we're going to look at our first carbon. So our first carbon has 1, 2, 3, 4 bonds. So 4 electron groups, 4 single bonds, 4 electron groups. That means that we are going to need 4 orbitals to put those electron groups into. So we need an S and 3 P. So our hybridization is sp3. If we look at the second carbon, we have 2 single bonds and a double bond, but a double bond counts as 1 electron group. So this would be 3 electron groups. We need 3 orbitals to put those electron groups into. So it would be sp2. So that means we're going to mix 1 s and 2 of the p orbitals to form a hybridized orbital on that carbon. That leaves 1 unhybridized p orbital to form the double bond to the oxygen. If we count our bonds, every single bond is a sigma. So our first carbon, we have 4 sigma bonds. Each single bond is a sigma. If we look at the second carbon, we've got another sigma to the hydrogen. We have 1 sigma to the oxygen and 1 pi. So we have a total of 6 sigma bonds and 1 pi bond. So when we say bonding scheme, we're talking about how many sigma and pi bonds that there are. Here's a practice molecule for you to try. It's already been drawn for the Lewis structures. Just be careful about the lone pairs on our oxygens. But predict what the hybridization around each atom is. So hydrogen cannot hybridize. Hydrogen only has s orbitals. So any of our 3 hydrogens is just an s orbital. If we look at our oxygens, so the red molecules are oxygens. Now our lone pairs are not drawn. We would have a lone pair, 2 lone pair on each oxygen. In order to make our 8 electrons, because we only have 2 single bonds. So our oxygen has 4 electron groups. Remember, lone pairs count as an electron group. So we're going to need 4 orbitals. We start with s, and we are going to need 3 p's. So each of our oxygens would be sp3 hybridized in this case. The boron, which is the gray or purplish looking atom, has 3 electron groups drawn around it. Remember, boron is all right with 3 bonds. So we have 3 electron groups, which means we have use an orbital in order to make our 3 electron groups. So we need 3 orbitals. We need sp2. So boron is going to be sp2 hybridized because it has 3 electron groups. Oxygen is sp3 hybridized because it has 4 electron groups. And hydrogen doesn't hybridize. It is just the s orbital. One more for you to practice on. See if you can predict the hybridization and bonding scheme for the atoms in NCIO. If we look at our oxygen has a double bond. It is also, in order to fill its octet, it is going to need 2 lone pairs. So our oxygen has 3 electron groups, which means that we need 3 orbitals to put those electron groups into. So it is sp2 hybridized. If we look at our nitrogen is showing 6 electrons. We've got 4 in the double bond to the oxygen, 2 in the bond to the chlorine. We are going to have 1 lone pair on the nitrogen. So nitrogen has got 3 electron groups. And so we need 3 orbitals to put those electron groups into. So this is going to be sp2 hybridized. If we look at our chlorine is going to have 3 lone pairs of electrons, 1 bond. So this is 4 electron groups. We need 4 orbitals to put them in. So the chlorine would be sp3 hybridized. Now if we look at our bonding scheme, we have a single bond and a double bond. So the first bond in the double is going to be a sigma. The second bond is going to be a pi. So in this case, we have 2 sigma bonds, 1 pi bond. It is always the case that single bonds are sigmas. The second bond in a double, or maybe I should say it, double bonds have 1 sigma and 1 pi, and triple have 1 sigma and 2 pi.